Hello everyone, welcome back to Airborne Education. Today we will talk about total drag, induced drag and parasite drag. Let's start with the induced drag. It's also called lift-induced drag.
Lift-induced drag is a byproduct of generating lift. When a wing produces lift, high-pressure air below the wing spills over the wingtip into the low-pressure region above, creating swirling vortices. These vortices tilt the total aerodynamic force backward, introducing a drag component parallel to the relative wind. The key factors affecting lift-induced drag are 1. Aspect ratio. Higher aspect ratio wings, especially if the wings are longer and narrower, reduce induced drag because the wingtip vortices have less influence over the entire span. Number 2. Lift coefficient. Induced drag increases with lift, especially at high angles of attack, like during takeoff or slow flights. Number 3. Weight and load factor. Heavier aircraft or those in high G maneuvers experience greater induced drag. Pilots minimize induced drag by flying at optimal speeds, near best glide or endurance speeds, and using high lift devices like winglets to disturb vortices highly reduce the induced drag.
And then we have parasitic drag.
Parasitic drag is the resistance that aircraft experiences that doesn't contribute to the lift. Essentially, it's wasted energy. Unlike induced drag, which is a byproduct of lift generation, parasitic drag increases with speed and comes from three main sources. Number 1. Form drag. Form drag caused by the shape of the aircraft. Air separates around uneven surfaces, creating turbulent wake regions. A streamlined design minimizes form drag. Number 2. Skin friction drag. Skin friction drag results from air molecules sticking to the aircraft surface. As we know, the air is sticky. Therefore, smoother skin, like polished composites, the skin friction drag becomes lower. Number 3. Interference drag. Interference drag happens when airflow disturbances from different aircraft components interact, like where the wing meets the fuselage. Proper fairings will reduce interference drag. Parasitic drag grows with the square of velocity. If you increase the speed by 2, the drag will increase by 4. That's why high-speed aircraft more focused on smooth surfaces, while slower planes can tolerate more draggy designs.
And that brings us to the total drag, which is the sum of all the drag types.
It's the combined effect of two primary components. 1. Parasitic drag. As we know, parasitic drag is the drag type that doesn't contribute to the lift, including form drag, skin friction, and interference drag. It increases with speed and dominates at higher velocities. Number 2. Induced drag. The drag created as byproduct of lift caused by wingtip vortices and the backward tilt of the lift vector. It's highest at low speeds, for example, during takeoff, and decreases as speed increases. The relationship between these drag types creates the total drag curve. And the pilots and engineers optimize aircraft performance by managing this balance, whether through wing design like aspect ratio, or speed adjustments, or drag reducing technologies.
Now we know the types of drag and how they affect the aircraft. Thank you very much for watching and see you on the next video. Take care.